Hello everyone, in this video we're going to be talking about surface tension, viscosity, and capillary actions, and they are all going to be the functions of intermolecular forces. So let's start out with the surface tension. The surface tension is defined as the energy required to increase the surface area by a unit amount. Every liquid has the tendency to kind of create a layer on the top of that so that it cannot be penetrated. For example, if I look at the water molecules, or let's just roughly talk about any molecules, if I got a bunch of these molecules right there, they're going to be making some sort of intermolecular forces with one another so that these layers cannot be penetrated. And that's what happens when the bugs sit on the water without even penetrating into the water, without even getting drowned into the water. That's because there is a thin skin of the top layer that cannot be penetrated. Now, if you have strong intermolecular forces, then you're going to have a stronger layer on the top that's going to be needing a higher energy to penetrate. Or another way of saying, the stronger intermolecular forces will give you an increased surface tension or give you more surface tension, and the opposite can be said as well, where you have the weak intermolecular forces gives rise to lower surface tension. You may have noticed sometimes if you're a big fan of fishing, if you throw the bait into the water and if it's not heavy enough and I got some feathers on it, it may just sit on the water without even getting inside the water first, and that's because of the surface tension. And you can probably have a paper clip floating on the water because of the same reason. Let's talk about the viscosity. Viscosity is going to be the property of the liquid that resists to flow. So a lot of times you have some liquids flowing better than the other ones. And we can take an example of honey versus water. Honey doesn't like to flow much, but you can have the water flow easily, and that's because of honey is more viscous than the water. What really determines which particular liquid is going to be more viscous than the other one is just the type of intermolecular forces. If you have a stronger intermolecular forces, the liquid is going to be more viscous compared to another one. Let's take two examples here. In this first example, I got the carbon chain with an OH and the middle carbon, and then in the second example, the example I'm comparing with, I got a carbon double bond O here. So what type of intermolecular forces will be made by this first compound, and what type of intermolecular forces will be made by this second compound? So the first compound, since it's got the OH, is going to be able to make hydrogen bonds, and then this second molecule does not have any hydrogen bonded with either oxygen, fluorine, or nitrogen. However, you do have this carbon-oxygen bond that's going to be polar, and as a result, it's capable of making dipole-dipole interactions. When you're comparing the interactions, or when you're relying on the type of interactions being made to determine which liquid is going to be more viscous than the other, you must be comparing the compounds that has similar molar masses, or they have similar in sizes. You can't really compare a compound with, let's say, 3 carbons and 12 carbons. That's going to be a little bit different, a little bit hard to compare just based on the type of hydrogen bonds or the intermolecular forces. Since the first one makes stronger intermolecular forces than the second one, the first one is going to be more viscous. Well, let's look at the second example. I got the gasoline versus the engine oil. So gasoline is C8H18. And as far as the engine oils or the motor oils go, they have the variations in terms of how many carbons they can carry. And depending on which one you're using, you could have the carbons anywhere between 24 or more. And since you have more carbons, if I just take a generic example and I say, okay, C24H50 in that case, their hydrogen numbers could be a little bit off here and there depending on how many rings you have in there. clearly I cannot rely on the type of intermolecular forces, but here I'm going to be relying on the strength of the intermolecular forces that are made. Since you have a bigger molecule, it's going to be making a bigger number of intermolecular forces, and turns out both of those has only carbon and hydrogen, so both of them will be making only dispersion forces because it's a nonpolar molecule. However, the dispersion forces made by C24H50 are going to be bigger in numbers, or are going to be more in strength, so more dispersion forces, and as a result it's going to be more viscous. Talk about this capillary action, and the capillary action is going to be the ability of a liquid to flow up in a narrow tube against the gravity. So you may have seen plants getting the water from the roots. So you don't really water the leaves, but rather you water the roots, and the water goes up against the gravity from the roots onto the leaves to perform or to do the photosynthesis process. And another example is the blood drawn into a narrow tube from the hand. Both of those are example of capillary reactions where it's actually going against the gravity, and why it really happens, it's technically based on two types of forces. The first force is called the adhesive force, and that's going to be the force between the different molecules. So it's also this force is also responsible to spread out the liquid. If I have water and glass, so if I'm comparing the interaction between the water and the glass, that's going to be your adhesive force because it's between the different molecules. On the other hand, your cohesive force is going to be between the same molecule. So another way of saying, I'm comparing the interactions between the two water molecules, and that's going to be your cohesive forces. As the name specify, the cohesive force is responsible for the liquid to keep it together. So that's one of the reasons water when it rains, it kind of rains in the form of a droplets. What really happens in case of capillary reactions, and I'll take an example of water first. In water, when the liquid is drawn up, it's got a stronger adhesive force than a cohesive force. So I'm going to write down your adhesive force is greater than the cohesive force. What that means, the water interact with the side of the glass, or maybe side of the wood in case of water going up the roots, is going to be greater. So let's say glass here is going to be greater than the interaction between the water molecules. So as a result, that water molecule likes the glass more, so that's why it tried to kind of go up the glass molecules from the sides, like in this case, and leaves kind of a concave meniscus in the middle. So anytime you have stronger adhesive forces than the cohesive forces, that particular liquid, when placed in the beaker or a narrow tube, it's going to make a concave meniscus, like in this case. However, if you have a stronger cohesive forces, so maybe I can just copy this down here and just flip the sign there. So we got stronger cohesive forces, then the molecules likes to stick with one another rather than sticking to something else. And a good example is mercury. And you may wonder in some of those movies where you have that Mercury Man, when you blow up the Mercury Man, how all that mercury kind of got together even after blowing it up. That's because mercury has stronger cohesive forces, so it likes to stick with its own mercury atoms better than the other ones. And if you do place mercury in this beaker or in this test tube, it's going to be making a convex meniscus where it's going to be trying to avoid this glass surface as much as it can. So that's why you got this convex meniscus here. So if you have a liquid or if you have a material that has the stronger cohesive forces than the adhesive forces, then it's going to be making a convex meniscus. Let me take another example where you see this adhesive and cohesive forces is the windshield. When you, back in the days, if you hammer the windshield, it will just splatter. But now, if you hammer the windshield, it's not going to splatter, but it's going to break slowly. And that's because you got stronger adhesive forces in that case, where the glass it's mixed up with some other material and they like to stick together. And that's why it's not like breaking or it's not splattering into pieces, but rather it's going to be very hard to break into the windshield in that particular case. All right, so those are the three common phenomena that you're going to be seeing for the liquids. If you have any questions, feel free to leave any comments in the section.